Hey guys, welcome back to Quick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Counting on Friends. It's a medium problem, and in my opinion, this problem is pretty clever. I really enjoyed this problem. So I'll let you guys pause and go over the problem once. So the hint given for this problem on the website is, in my opinion, perfect. It basically says the pigeonhole principle. That's just a fancy way for talking about a theorem which says that, let's say you've got n different slots, right? And you've got n plus 1 different candies that you need to put in each slot. Now, the theorem says that you will have to choose at least one of these n slots that will include more than one candy. Why is this? Well, if you were to try your best, you could distribute n of these n plus 1 slots or of these n plus 1 candies into each particular slot so that each slot has one candy, but then you're left with one more candy. So at least one of these n slots is gonna have to. So let's say we just choose this one. This slot is gonna have to have more than one candy. So the theorem basically says that if you've got n plus 1 different items and you want to distribute them among n slots, then at least one of these n slots is going to have a storage value of greater than 1. So let's focus on the line given to us that we have to prove, and that is that there are at least two people with the same count of friends. Well, we'll be solving this problem using proof by contradiction. So let me just write down the contradiction statement over here. So yeah, so there you go. So basically, if we have to prove that there are at least two people with the same count of friends, well, the contradiction would be that every single person among these n people have a different value for their friends count. And friends count basically just means the number of friends that the individual has. Now, if we observe this value over here, friends count, also consider the fact that there are n people in total in this party, the friends count variable could take up values from 0 all the way up to n minus 1. Now, why is that? Well, because for a particular person, he could either befriend 0 people or 1 person or 2 people all the way up to n minus 1 people. Now, you might think, why can't the friends count value be equal to n? Well, it can't be equal to n because he can't befriend himself. Other than that single person, there's n minus 1 other people in the party that he could potentially befriend, right? So the value of friends count can only go up to n minus 1 since he can't befriend himself. So this means that the friends count variable has a total possible number of values of n, a total different possible outcomes of n, right? Now, the other thing that we have to realize is, since there are n people, as mentioned over here, and our assumption states that every single one of those n people have a different value for the friends count, and the friends count can only have an n different values. That means that there is only one configuration that is possible that would satisfy the given assumption, and that would look something like this. This is the only configuration that would satisfy the given assumption. Why is this? Well, this over here, so I've assumed that this is P1, this is P2, all the way up to Pn. And I've assigned the value of the friends count for each individual person. And so person 1 has befriended 0 people, person 2 has befriended 1 person, all the way up to Pn. And because each and every P value of Pi has to have a different value of friends count, Pn has to be befriending n minus 1 people, right? Now, the problem with this particular configuration is this value and this value. These two contradict themselves, each other. Why is this? Well, this is because we're saying that P1 has befriended nobody at all, since P1 has befriended 0 people. But at the same time, we're saying that Pn has befriended all n minus 1 other people. And according to the definition of a friendship, which is symmetrical, if A is friends with B, then B is also in turn friends with A. Now, this is not possible that one person has 0 friends, while the other person is friends with each and every other person of n minus 1, would mean that Pn is friends with P1. But P1 can't be friends with anyone. So this particular configuration is not possible. And if this particular configuration of 0, 1, 2, all the way up to n minus 1 and n minus 2 is not possible, then our assumption is not possible, because this is the only configuration according to the pigeonhole principle which would satisfy our given assumption. And if our assumption is wrong, then our contradiction is wrong. And if our contradiction is wrong, then we have proved the given statement that there are at least 2 people with the same count of friends. I've also provided the written solution on the website. I recommend you guys to go over it, and I hope you guys understood the solution. So thanks for watching.